Ever find yourself in a tunnel and wonder, what's keeping this from caving in on me?
It's a thought, isn't it?
Today's deep dive is all about the unsung heroes of underground construction rock bolts.
We'll be focusing on one particularly ingenious type, the D-bolt.
And get this, we'll then journey from securing tunnels to the elegant world of math, exploring how screws, twists, and wrenches help us understand motion in a whole new way.
It's quite a ride, from practical engineering to mind-bending mathematics.
You always send the most intriguing source material. We've got these reports on rock reinforcement and then mathematical papers on the geometry of motion. It's like, how do those even go together?
You'd be surprised how connected those two worlds really are.
Okay, well, before my mind explodes from the suspense, let's start underground, shall we? Imagine you're deep in a tunnel, tons of rock pressing in from all sides. What's stopping it from becoming, well, a much flatter experience?
That's where rock bolts come in. They're essentially steel rods drilled deep into the surrounding rock, kind of like giving the tunnel walls internal stitches.
Stitches that hold the world up. Got it. But we're talking about a special kind of rock bolt, the D-bolt. Why the fancy name? What makes it so special?
It's all in the design. Unlike a traditional rebar bolt, which is a single solid rod, the D-bolt is made up of several shorter sections connected end to end.
Okay, so segmented. I'm seeing where you're going with this. It's like more bendy, right? But why is that a good thing deep underground?
Rock might seem solid, but at those depths, it's constantly shifting and deforming. The pressure is immense.
Ah, so like a chain versus a single rod, the chain is more likely to, what, go with the flow?
Exactly. Each section of the D-bolt can move slightly independently, responding to these shifts in the rock. That's where its strength lies.
So it's not about resisting the movement, it's about working with it.
Precisely.
Now that is a clever engineering solution. Who knew rocks were so, well, flexible?
Not all rocks are created equal, and understanding the specific challenges of an environment is crucial for good engineering.
And speaking of understanding challenging environments.
And speaking of challenging environments, get ready to have your mind twisted.
Oh, I am always ready for that.
In a good way, of course.
Of course, because from stabilizing tunnels with cleverly designed rock bolts,
We're about to take a sharp turn into the world of mathematics.
bring on the numbers.
Prepare to enter the realm of screws, twists, and wrenches.
Okay, now you're just messing with me.
But don't worry, we're not talking about your toolbox here.
So no need to find my wrench.
No, these are mathematical concepts.
Oh, okay, so like theoretical screws and wrenches.
Yeah,
Got it.
exactly. We're going to explore how these concepts help us understand the motion of rigid bodies in a whole new way.
All right, lay it on me. What exactly is a mathematical screw?
Picture a corkscrew going into a wine bottle. It's rotating,
Right, twisting into the cork.
but it's also moving linearly downwards.
Ah, so it's not just spinning, it's like moving forward while spinning.
Precisely. That elegant combination of rotation and linear movement, that's the essence of a screw in this context.
Okay, I think I'm starting to get it. So how does this corkscrew idea apply to something bigger, like a moving object?
Imagine any rigid body moving. It can rotate around any axis, translate in any direction, or do a combination of both.
My head's spinning just thinking about all those possibilities.
It seems chaotic, right? But here's where it gets really cool. Just like we can represent any force acting on an object with a single resultant force.
Okay, makes sense.
We can represent any complex motion of a rigid body as a single twist about a specific screw.
Hold on, so you're saying no matter how complicated an object's movement is, it can always be simplified to one twist around a specific screw.
Exactly. It's a powerful concept.
That is really cool. So where do the wrenches come in?
Ah, yes, wrenches. Think of a wrench as a force applied along the axis of our imaginary screw.
So like when you use an actual wrench to tighten a bolt, it's a twisting force.
You got it. We use wrenches to represent forces acting within this system.
So we've got twists for motion and wrenches for forces. It's like a whole new vocabulary for movement.
And just like any language, it has its own grammar and syntax.
You mean there are rules for how these screws and wrenches interact?
Exactly. There's a whole algebra for screws. Just like we have algebra for numbers, we can add them, subtract them, even multiply them.
Wait, really? So we can do math with these theoretical screws and wrenches?
Absolutely. This allows us to understand how forces in motion are connected in a very precise and elegant way.
My mind is officially blown. We've gone from D-bolts holding up tunnels to doing algebra with imaginary screws and wrenches. It's amazing how these abstract mathematical concepts can have such real-world applications.
It gets even more interesting.
You mean it gets even more mind-bending than doing algebra with screws?
Oh, yes. Because remember those harmonic screws we mentioned earlier?
Harmonic screws. Okay, you're right. It does get more mind-bending. Those sound pretty wild.
They're key to understanding how objects vibrate.
All right, you have my full attention. Tell me more about these harmonic screws and how they relate to vibrations.
Imagine flicking a crystal wine glass. It makes that ringing sound, right?
It's like that delicate ringing, yeah.
That specific tone is its natural frequency of vibration, and every object has these frequencies at which it likes to vibrate.
So it's like each object has its own set of musical notes.
In a way, yes. And these harmonic screws help us describe and understand those frequencies.
Okay, I'm with you so far. But how does this apply beyond tuning forks and wine glasses?
It's crucial in fields like mechanical engineering, robotics, you name it.
So we're talking about designing things like bridges and buildings, making sure they don't fall apart.
Exactly. We need to understand how and at what frequencies a structure might vibrate.
To avoid a catastrophic symphony of destruction.
Precisely. We want to make sure structures can withstand the vibrations they might experience.
That makes sense. Now, going back to something you mentioned earlier, this whole non-Euclidean geometry thing, it's still swirling around in my head. You said we could apply screw theory to that.
It's a mind-blowing idea, right?
More than a little. It sounds like something out of a science fiction novel. Can you give us a simple example?
Imagine you're an ant living on the surface of a donut.
A donut. Okay, I'm intrigued. This is going to be good.
To you, as the ant, the world is curved. You could walk in what you perceive as a straight line, but to an outside observer, you'd be traveling in a circle?
Because the donut itself is curved. So our perception of straight lines depends on the space we're in.
Exactly, and that's non-Euclidean geometry. It governs spaces that are not flat, like the surface of our donut, a sphere, things like that.
Okay, I think I'm wrapping my head around that. But how does screw theory fit into this curved world?
Mathematicians believe we can extend those principles of twists and wrenches to describe motion in these non-Euclidean spaces.
So not just how objects move in our regular 3D world, but on curved surfaces and in different dimensions.
Exactly. It could change how we design robots, understand the movement of particles in space-time, even how we view the universe.
Wow, so from stabilizing tunnels to potentially unraveling the mysteries of the universe, all thanks to these elegant mathematical concepts. That's the beauty of a good deep dive, isn't it?
It really is. You never know what connections you might find or where they might lead.
Well, on that note, we've journeyed from the depths of the Earth with those remarkable D-bolts all the way to the mind-bending world of screw theory and non-Euclidean geometry. It's been quite the adventure. Until next time, keep those brain gears turning, everyone.